Hey everyone, today we start talking about logarithms, and a logarithm is really just a mathematical way of answering the question, what is my exponent? So for example, if we have this logarithmic function given here, what it's really saying is a to the power of y is equal to x, meaning if I raise my base to what power, that's what I'm looking for, will I get this number as an answer? So if you can keep that in mind, I think it'll make logarithms a little bit simpler. So basically it's answering the question, what power would I raise my base to equal this number right here? So because of that, we can also express it as an exponential function as well. So this number here becomes the base of our exponential. This number is our exponent, and this number is what it's equal to. So we can convert back and forth in between them. Because that's the case, then these properties are true of logarithms, and these properties are true of the natural log. So ln stands for the natural log, and we first learned about the base e when we talked about exponentials, because it's used a lot in real-world functions. So anytime you have a logarithm with a base of e, we call that the natural log, and we write it with an ln. So basically, because a logarithm is answering the question, what's my exponent, this is saying a to what power would equal 1? Well, anything to the 0 power is going to be equal to 1. So anytime you're taking the log of 1, the answer is going to be 0. Anytime your log and your number match, then the answer is going to be 1, because any number to the first power is going to be itself. And so for that matter, anytime you have matching bases here, they will cancel each other out. In other words, logarithms and exponential functions are inverse operations of each other. And we can see it written this way as well. And if we are ever given matching logs on either side of the equation, then whatever it is that they're equal, whatever the number is, they must also be equal. So we'll talk about what that's going to look like. These are the same matching properties with the natural log. So if we take a look, we can evaluate logarithms that were given by plugging in numbers, whatever they give us for x. So if they want us to find f of 32, it's saying 2 to what power, meaning what's my exponent? 2 to some power would equal 32. Well, that would be 5. So the log base 2 of 32 would be 5. And you could also do this in your calculator, but it's really easy to do if you just think about what a logarithm means. Remember how we talked about the log of 1 is always going to be 0, because no matter what the base is, when we raise it to the 0 power, it equals 1. Here we have, again, let's think about it, 4 to some power equals 2. Well, the square root of 4 is 2, and the square root can be written as an exponent to the 1/2 power. Roots are how we get what are called rational exponents, or exponents that can be written as a fraction. And in this case, we have log of x to the 1/100th, and we don't have a base. And so what we need to keep in mind is that when we don't have a base that's written, it's either a natural log, ln, but in this case it's not a natural log, it says log, then the base is always 10. So if we rewrite this as an exponential, 10 to what power would equal 1/100? Well, 1/100 is the same thing as 1/10 squared. And to get that reciprocal, we use a negative exponent. So these don't work out as nicely. Well, a does actually. Log of 10, well, those are matching bases, so that would equal 1. But in this case, log of 2.5, we would have to evaluate in our calculator and round. So we can literally just type it in our calculator, log of -2, or log of 2.5, or log of 1/4, and get that straight from our calculator. So here I tried to color coordinate the properties with the problems that you could see them. So evaluating logarithms, this was all based on this kind of converting between logarithmic and exponential form. If we take a look at example 3, we're going to try to apply some of these properties. So it's saying that log base 2 of x equals log base 2 of 3. So if we have matching logarithms on both sides of an equation, then they can cancel each other out like we have here, or you can see I color coded it here. This is the exact property. Then we can drop the logarithms and the two numbers are equal to each other. So we'll use that in the future to solve logarithmic equations when we get to that. Here we are taking the log of 4 with a base of 4. So 4 to what power would equal 4? Well, that would be to the first power. Remember, a logarithm is always asking what's our exponent. So here we have 5 to some power would equal 5 to the x. Well, we would have to raise it to the x power. Or in other words, these would cancel each other out. And then here we have a logarithm that's written in an exponential function, but they have matching bases, so again, they would cancel each other out, leaving us just with 14. So graphically, logarithms are the reflection across the line y equals x of exponential functions with the same base. So if I were to graph log base 2 of x, it would be the reflection across the diagonal line of the exponential function 2 to the x. So this is 2 to the x graphed, and this is the reflection of it, or another way to think about it is we swap all of our x and y values. So if we have a point in our 2 to the x function at 0, 1, we're going to have a point at 1, 0. And if we have a point at 1, 2, then we'll have a point at 2, 1. And if we have a point at 2, 4, then we would have a point at 4, 2. And so instead of having a horizontal asymptote, we now have a vertical asymptote. This is going to be important. Knowing this vertical asymptote means that we have a restriction on our domain, which means when we solve equations, sometimes we will get extraneous solutions or answers that don't make the actual logarithmic function work. This is a log with a base of 10, so to graph this easily, you'd probably want to change all of the numbers on your x-axis to have a scale factor of 10, just so you could fit more than one point. But if we do that, then our original function, it's hard to see, is graphed right here. And then if we shift to the right one, we would get g of x. And if we were to shift up 2, we would get h of x. So all of the transformation rules stay the same. So anything grouped inside parentheses with our x is going to shift, or it's going to transform, I should say, horizontally. And anything outside parentheses would affect the graph vertically. Okay, so here we're just evaluating, or we're plugging in for x again. So we're using the natural log this time, which is a button on your calculator, just like the log button was. And this was just a matter of plugging in this into the calculator and then rounding. And then here we're applying those same properties, but with the natural log. So in this case, we have the natural log of 1 over e, which is the same thing as saying the natural log of e to the negative 1 power. A natural log has a base of e, so the matching bases would cancel each other out, leaving us just with negative 1. Same thing here. Here we're taking the natural log of 1, which, remember, anytime we do that, it becomes 0. So we have 4 times 0, which would be 0. And in this case, we have the natural log of e, which would be 1, and we're multiplying it by 2, so we would get 2 for an answer. And these, again, are all things that you could also put into your calculator, but they're really easy to do if you follow the properties. Okay, so we talked about how domain of logarithmic functions could be restricted because of the vertical asymptote now. So the range will always be all real numbers for these, but the domain is going to be wherever that vertical asymptote is. So in this case, we've shifted to the right 2. So normally our domain would be x is greater than 0, but because we've shifted, it's now going to be x's that are greater than 2. You could write it either way, in set notation or in interval notation. Both are acceptable. In this case, we have to be careful because our x is being subtracted. So really what we're doing is we're reflecting horizontally and we're shifting horizontally. But to find the true shift, we have to factor out that negative. So actually we're shifting to the right too, and we're also reflecting horizontally. So now instead of the graph going to the right infinitely, it's going to go to the left infinitely. So it's all of our x's that are less than 2. And again, you could also get this by graphing it and then looking and see where your graph is occurring. In this case, I would suggest doing this one by graphing, and you can see it's almost a reflection on either side, so it's all of the x's, just not at 0. So you could write it in either fashion in that case. In number 10, we're applying a word problem. So they're giving us a logarithmic function that is being modeled in this graph over here of basically the student's memory of test material over a certain number of months. So the average score on the original exam, meaning after 0 months, was, if we plug in 0, we get 75 minus 6 ln 0 plus 1. We simplify that, we get the natural log of 1. Remember, that becomes 0, so it becomes 75 minus 0, or just 75. The average score at the end of 2 months, if we plug that in, we can put this into our calculator, 75 minus 6 ln 3, and we get about 68.4. So we can see that the score is going down a little bit. And after 6 months, the score would go down a little bit more. But it's just kind of problem solving with that natural log. So what I'd like you to be able to do is graph logarithmic and natural log functions given different bases. I'd like you to be able to transform the graphs, and I'd like you to be able to evaluate natural logs, or either by converting into exponentials or by using different properties or your calculator. And if you can do those things, you should feel very comfortable with this section of information. If you have any questions, please, please, please make sure that you ask them either through email or in our weekly optional help sessions, whatever you prefer, and check out some of those practice problems. I'll see you guys later.